So welcome to my channel on technology space with machine learning and artificial intelligence. So today I am starting a new playlist called Maritime Technology. So just to prepare for that approach, I'm introducing some terminologies in the maritime industry in this presentation. So let's move on to the main topics of this presentation. So let's further emphasis on why this is important. As I have mentioned that I am starting a new playlist on maritime technology that further will be developed under this channel. So I would discuss various topics related to the maritime technology under this specific playlist. And eventually I will merge this, the main topic of digitalization with maritime technology in the future. So let's move on to the main content of this presentation. So let's introduce the two terms of bow and stern. Bow is the front of the vessel and the stern is the rear of the vessel. So the next term is the center line. When you draw a straight line from bow to stern, the center of the vessel, through the center of the vessel, then that line is called the center line. So we can assume if we draw a vertical surface along the center line that could divide this vessel into two sectors, and these two sectors are symmetrical to each other. So the next two terms would be port and starboard. So the port is the left side of the vessel and the starboard is the right side of the vessel. So let's introduce the two terms of mass and weight. Mass can be defined as a measure of the amount of matter in any object. In this case, the vessel is our object. And when you multiply mass times the gravitational constant, that will give you the weight of the vessel. So in this figure, you can see mass I have denoted as M for this vessel, and the vessel weight is denoted as W, and which is equal to the M times the gravitational constant of G. So since we have discussed this weight of the vessel, I would introduce three additional terms. The first one is light displacement or light ship weight. So the light ship weight is the actual weight of the vessel when it is ready for service but empty. And then the second term would be dead weight. So the dead weight represents the total load of that specific vessel. That includes the cargo it's carrying, stores, fuel, and etc. And when you add up this dead weight and the live ship weight, that would give you the total displacement of the vessel. So that means that you can consider as the total weight of the vessel itself. So here I'm introducing the next term of center of gravity. So the center of gravity for this vessel is where the total weight force of the weight force is considered to act vertically downwards. So this is a specific point where this weight force is acting downwards. And since we have mentioned that load condition of the vessel, so you can imagine under different navigation conditions, these vessels may have different load conditions. So because of that, the total mass in that vessel will change. So due to the same reason, the center of gravity will also change. I would introduce additional factors that will involve in this process to change the center of gravity. Because of this variations in the center of gravity, I am introducing a new terminology into this discussion. It is called this apparent center of gravity. And I would use this terminology throughout my presentations. But you should know why I have introduced this terminology, because due to various conditions, the center of gravity of these vessels will change. So because of that, we are introducing this new terminology of apparent center of gravity in this discussion. So let's discuss some terminology related to ship motion. So the first part of that discussion would relates to this translational motion. Translational motion can be defined as a situation a moving rigid body moves uniformly in the same direction. That means no rotational motion get associated with that rigid body itself. In such situation, actually you can approximate a rigid body into a particle which consists of that center of gravity of that rigid body. So the first term we're going to introduce under that translational motion would be surge motion. Surge motion can be defined as the translational motion along the longitudinal axis that runs from stern to bow through the apparent center of gravity. In this figure, I am representing this xga as the longitudinal axis and the surge motion as u. And also the apparent center of gravity is represented by CGA for this vessel. So the next term would be sway motion. So the sway motion can be defined as a translational motion along the lateral axis that runs from port to the starboard side through the apparent center of gravity. And in this figure, I'm representing this sway motion by V, and YGA represents the lateral axis for that vessel. So the last translational motion would be heave motion. So the heave motion can be defined as the translational motion along the vertical axis that runs parallel to the weight through the apparent center of gravity. In this figure, I am representing the heave motion by W, and then the vertical axis is represented by ZGA. So, so far in this discussion, we have mentioned three axes in this study. So those are the longitudinal axis, lateral axis, and the vertical axis. You should also note that these axes are perpendicular to each other to represent vessel motions in a three-dimensional space. So these three axes can also be considered as a coordinate system which satisfy the right-hand rule. And I would discuss these coordinate systems and the right-hand rule in separate discussions on vector spaces in a future video. So let's move on to the additional terminology in this ship motion section. Here in this section we are going to discuss the rotational motion. So the rotational motion can be defined as a situation, a rigid body moving in a circle around a fixed axis, and it has a uniform rotation with a common angular velocity. And the first term in the rotational motion we are going to introduce this case is the roll motion. So the roll motion can be defined as the rotational motion around the longitudinal axis. In this figure I am representing the roll motion as a P. And the next terminology would be the pitch motion. So the pitch motion can be defined as a rotational motion around the lateral axis. In this figure I am representing the pitch motion by Q. And finally the rotational motion around the vertical axis can be defined as the yaw motion. And the yaw motion I am representing in this figure by R. So since we have discussed three translational and three rotational motion for that vessel, let's try to discuss the concept of a degree of freedom, or DOF. So the degree of freedom can be referred to as the number of basic motions, translational and rotational, that a rigid body or a rigid object can have through the three-dimensional space. So in this example of the vessel, we have mentioned three translational motion, surge, sway, and heave, and three rotational motion, roll, pitch, and yaw. So now you can imagine it has three translational motions and three rotational motions. We can define the degree of freedom for ship motion as the total number of these motions, which is equal to 6. So here I am trying to introduce additional terminology which may more related to the nautical science, but I would think that's also important for that discussion. So the first concept would be the heading or the heading vector. So the heading vector can be defined as the direction where the ship bow is pointing with respect to the true north. So the surge and the heading vectors are in the same direction. And in this figure I am representing the heading vector by H, and its angle is represented by psi. So in generally, these heading vectors can be estimated by fiber optic gyroscopes, because those are doing a pretty good job on estimating the heading vector accurately. Most of these inertial measurements and sensors measure this heading vector based on the magnetic field of the Earth. That may not be that accurate in some situations. But I would open up another discussion on the sensors that can be used in this vessel. So in that video, I would discuss more detailed version of these parameter estimation for these ocean-going vessels. So let's move on to the next concept of course speed vector. So the course speed vector can be defined as the direction where the vessel is traveling at its speed. So here we introduce the speed as the speed over ground. In some situations, the heading and the course speed vectors may have different directions. I think that deviation will create some level of challenging when you're controlling vessels by rudder and propeller control system. The course speed vector is represented by V in this figure, and the course angle is represented by chi. And there are GNS sensors that can estimate this course speed vector somewhat accurately in ship navigational situations. So since we have discussed that speed over ground concept in the previous slide, let's elaborate that is further. So the speed over ground represent SOG. So that can be defined as the vessel speed reference to the surface of the Earth. As I have mentioned, GNSS sensors can be used to estimate that SOG values for these vessels. And then there's another speed for these vessels that is called the speed through water, STW. So the speed through water is the speed of the vessel reference to the water. So if a vessel navigating in a larger water surface which is moving in a specific speed, for example under ocean current conditions, so then the vessel will have that speed through water. So the speed over ground and the speed through water will have two different values. So that means you are measuring the speed of the vessel with relative to the speed of the ocean current at that specific situation. So we can use Doppler log sensors to estimate that speed through water in these situations. So the last term I'm going to introduce in this presentation would be the drift angle. So we have mentioned that in some situations the heading vector and the course speed vectors will have two different directions. Because of that reason, when a vessel pointing towards even though a vessel pointing towards the specific direction, it might drift towards another direct direction. So obviously there's a drift angle in between these two vectors. So the drift angle can be defined as the angle between heading and the course speed vector. And in this figure I'm representing beta as the drift angle, which is equal to the chi minus psi in this figure. So that's the end of my presentation. Hopefully you have enjoyed this new playlist. And so if you are still interested, please stick around. Thank you.